In chapter number 6 of this course, we talk about the interpretation of execution plans, and we're going to discuss certain execution plan enhancements. After you have completed this lesson, you should be able to interpret execution plans, and you should be able to discuss adaptive optimizations. The first topic of this chapter is the interpretation of a serial execution plan. Now, an execution plan is a representation of a tree of row sources. Each step, represented by a line in the execution plan or represented by a node in the tree, represents a row source. The explain plan utility indents nodes to indicate that they are the children of the parent above it. The order of the nodes under the parent indicates the order of execution of the nodes within that specific level. If two steps are indented at the same level, the first one is executed first. In the tree format, the leaf at the most left side of the tree is where the execution will start. Now, the steps of the execution plan are not performed in the order in which they are numbered. There is a parent-child relationship between steps. Now, in the plan table, or in VDAL or SQL plan, the important elements to retrieve the tree structure are the ID, parent ID, and the position column. In a trace file, these columns correspond to the ID, parent ID, and position fields respectively. One way to read an execution plan is by converting it into a graph that has a tree structure. When building that tree structure, you always start from the top with the row source with ID number 1, which is always the root node in the tree. Next, you must find the operations that feed this root node. So if I'm taking a look at this slide, the row source step with ID 1 is always your root node. Then you will have to find out which other row steps feed the row source with ID 1. And in this case, the row source step with ID 2, as well as the row source step with ID 7, they feed row source step number 1, with the row source step ID 2 at position 1 and row source step with ID number 7 at position number 2. Then you're going to see which row source steps will feed ID number 2. And what I'm saying is that row source step ID number 3 and row source step ID number 4, they feed row source step number 2. So ID number 3 is actually this child leaf node at position number 1, and parent-child node with ID number 4 feeds row source step number 2, but put at position number 2. And this is how you're going to convert your execution plan into a tree structure. Now let's have a couple of examples, because the steps of an execution plan are not performed in the order in which they are being numbered because of the parent-child relationship between steps. So let's say the following example. Let's say I have here a select statement, and this is the corresponding execution plan that has been rendered. Well, indentation plays a very important role, as well as the ID of the row source step. Now, what you do is you look for the row source step where the ID is 1, and that is actually the root node of your tree. So you put this at the top of your tree structure. Then you have a look which row source steps are indented directly underneath this step number 1, and in this case it's step number 2 and step number 6. So this is at level number 2, you have your step number 2 and you have your step number 6. Then you look at which steps are indented underneath step number 2, and if I'm looking at my execution plan, that is actually step number 3 and 4. Then you have a look which steps are indented underneath step number 6. There are no steps. Then you're going to have a look which steps are indented underneath step number 3. None. which steps are indented underneath step number 4, and that is step number 5. And this is how you convert this execution plan into a graphical tree structure. And then what you need to do is you start from the top of your tree and you always walk to your left until you can no longer go to your left. So this is step 1, go to the left, that's step number 2, go to the left, that's step number 3, and here I can no longer go down in the tree and go to the left. Well, this is then going to be your start point of the execution plan. So in this case, it will first carry out step number 3, and the rows that it produces, it gives it to step number 2. But step number 2 says, yeah, but I cannot start working if I do not get also the result of step number 4. And step number 4 says, yeah, but first I have to get input of step number 5. So after he has done step number 3, he will then perform step number 5, then step number 4. The row sources that 3 and 4 generate will be given to step number 2. Step 2 does its work, gives it to step number 1, but step number 1 says, look, I cannot do anything if I do not first receive the data also from step number 6. So you will then carry out step number 6 to finally carry out step number 1. So the right execution order is here, step 3, step 5, step 4, step 2, step 6, and step number 1. So this is a first example on how to interpret an execution plan. There's another example. So I have here a certain select statement, and this is the generated execution plan, in fact. Well, you have exactly the same story. Look for the row source step with ID number 1. That is always the root node of your tree structure. So you put this at the top. Then you're going to have a look which steps are indented directly underneath that step number 1. Or you can look here simply what is the parent ID. So you see that step number 2 and step number 7 are indented or are childs of step number 1, in fact. Then you're going to have a look. Yeah, but step number 3 is a child of parent ID number 2 as well as step number 5. So you have 3 and 5 underneath this level. Then you have this step number 4, which is indented or which is a child of step number 3. And then we have step number 6, which is indented underneath 5, or the parent is 5, in fact. Yeah, and this is how your tree structure looks like. And then to determine the execution order, when you have your tree structure, you always go down, starting with step number 1, and go to your left until you can no longer go down and to your left. So if I'm walking down that tree structure, step 1, go to the left, step 2, go to the left, step number 3, then go down and or to the left, and I'm reaching step number 4. Well, that step number 4 is your first step that will be executed. So he executes step number 4, produces rows, gives it to step number 3. So that's the second step that he will execute. 3 gives it to step number 2, but 2 says, yeah, but I cannot work without having also the rows produced by step number 5. And 5 says, I cannot do anything if step number 6 is not done. So he will start with 4, then 3, but then he has to do 6, then 5, and then he can start with step number 2. Now the rows produced with step number 2 are given to step number 1, but 1 says, yeah, but first I also need the row sources of step number 7 before step number 1 can then take place. So in this case, the correct execution order is 4, 3, 6, 5, 2, 7, 1. Now there's a third example showing how to interpret an execution plan. Now what do you have is that I have here my select statement. This is the execution plan that has been generated by using the parent ID, the child ID, and the indentation. I can come up with this tree structure, in fact. Now what will happen is I start at the top go down and to the left until I can no longer go down and to the left. So I'm having here step number 3 that will be executed first. And the rows produced by step 3 are given to 2. But 2 says I cannot work without having the rows produced by 4. And 4 says, yeah, but I need to first get the rows of step number 5 and 6. So he will carry out first 3, then step 5, then step 6, then step 4, then step number 2, and then step number 1. Now here, depending on the tool that you're using, it can actually show you the order in which the steps of an execution plan are being carried out. So by reading this tree structure and going down and to the left in my tree structure, I know that step number 3, which is the table access, full table scan of table T3, that's the first step that is being executed. Well, you see here order 1, well, that's that full table scan of T3. And then I've told you when looking at the tree structure, he will do step number 5 and then step number 6, which is full access for table T1 and T2. Well, you see here, the second step executed is the full table scan upon T1. Third step is the full table scan of table T2. So this is another example in determining the right execution order of each step within an execution plan. There is even a fourth example, is I have here a select statement. I'm displaying the execution plan, and this is the execution plan that is generated. Now, this is very easy to determine what he will do first. Well, he will start with an index range scan of index inventory index, and the row IDs that are being picked up via that index will be used to access the table inventories, and the rows that are being accessed are being returned to that select statement. Now, we have already seen in one of the previous chapters that when the optimizer is going to build up an execution plan, he's going to make an estimation of the number of rows it thinks are going to be retrieved by that select statement. It's an estimation, in fact. Now, what you can do is, if you're going to decorate your select statement with the hint gather plan statistics, you can then display the execution plan to show all statistics. So not only the estimated statistics will be shown, but also the actual execution statistics are going to be shown, giving you the possibility to compare the number of rows that the optimizer has estimated that will be returned by a select statement and the actual number of rows that are being retrieved. Now you see here that his estimate of records being returned is much higher than what was actually returned. So you can ask your question yourself, did the optimizer really made the best decisions in generating this execution plan? Now the second bullet is, which tools do you have to look beyond execution plans? Now an execution plan alone cannot tell you whether a plan is good or not, because the type of table that you're going to use or the type of index that you have created will also greatly influence the performance of the execution of an SQL statement. So maybe you will have to perform some additional testing and tuning. For that you have several tools like the SQL Tuning Advisor, the SQL Access Advisor. You can use the SQL Performance Analyzer to see what the effect is of a change that you have made upon a collection of SQL statements. You can use real-time SQL monitoring, you can trace, you can even make use of adaptive execution plans. But an execution plan on its own does not tell, okay, this is a good or this is a bad plan, but there are tools that can help you analyze this. Now there is a quiz. Now you want to carry out a select statement upon table inventories and you want to obtain those records where warehouse ID equals 1. Now what they're stating on the slide is that suppose that your table has in total 1112 rows and that the number of distinct values within the column warehouse ID is 9. Now your optimizer is first going to calculate the selectivity. That means It's going to calculate how big the chance is that if you pick one record out of the table, the warehouse ID will be 1. Now, because there are 9 distinct values detected in the warehouse ID column, the selectivity will be 1/9. Now, once he has determined the selectivity, he's going to calculate the cardinality. He's going to estimate how many rows it thinks are going to be retrieved by that select statement. Now, to calculate the cardinality, you take your selectivity, which is in this case 1/9, multiply that with the number of rows. If you do that calculation, this is 124 records that the optimizer thinks are going to be retrieved by that select statement. And based upon that, apparently the optimizer has concluded to use an index range scan as the most optimal execution plan. However, when I execute this, only 36 rows are being returned. So his estimation is showing a big discrepancy between the actual number of rows being returned. This example shows that the issue might be caused on how the data is being distributed in that column warehouse ID. Now, the last topic of this chapter is the so-called adaptive query optimization, which is something that was introduced as of Oracle 12c. But what is adaptive query optimization? Now, what you have is that whenever you're going to execute an SQL statement, the optimizer first has to build an execution plan, and then with that execution plan, the statement gets executed. Now, once the execution plan has been determined, that is the execution plan used for the execution, in fact. Yeah, but if the optimizer makes the wrong assumptions and comes up with a suboptimal execution plan, this can lead to a badly performing SQL statement. But he's no longer capable of changing the execution plan once the statement started executing. Now, in 12c, you have adaptive query optimization, which is a set of capabilities that enable the optimizer to make adjustments at runtime to the execution plan and discover additional information that can lead to better statistics, and even at runtime, change the execution plan, which is much more optimal than the initial one that has been chosen. That adaptive query optimization is extremely helpful when existing statistics are not sufficient to generate an optimal plan. Now, first of all, to use adaptive query optimization, the parameter optimizer features enable has to be set to 12.1 or later, and the optimizer adaptive reporting only initialization parameter is set to false. So if reporting only is false, it means that the mechanism is in effect. If you put optimizer adaptive reporting only to true, then this adaptive query optimization will not be active. Now, what can be changed or what can be adjusted at runtime? That is the join method. So the method to be used to join is deferred until runtime. So what you will have is that whenever you execute a statement with a join, the optimizer will come up, as always, with a default plan using the available optimizer statistics. However, the optimizer will also calculate some alternative subplans and store that in the cursor. Plus, also in your execution plan, statistics collectors are being inserted, and whenever certain values are being breached of those statistics collector, he can adapt the join method. For the moment, he can only change the join method nested loop to has join if needed at runtime. But the final decision is based upon statistics collected during the execution, in fact. So if the statistics that are being collected during execution prove to be out of range with the estimates that he has made, the subplans can be swapped. So he can switch, for instance, from a nested loop to an has join. This requires buffering near the swap point to avoid returning rows to the user. Now let's say that you're going to execute this query where you're performing a join between two tables and you want to find all products with a unit price of 15 that were sold more than once. Well, the optimizer is going to, if adaptive query optimization is active, the optimizer is going to consider two possible plans. He says we can use a nested loop or we can perform the join via the hasJoin method. Now what's going to happen is that the optimizer says, I think based upon the statistics that I have noticed, that the nested loop is the best way of performing this join. However, what you will get is when he starts scanning the first table, there is a statistics collector that is going to collect how many records have already been returned by the table scan of the very first table during a nested loop. Now, if the statistics collector says, yeah, but already more than 100 rows are being read by the first table scan, in fact, I think that nested loop is not a good idea. And during the execution, because the statement is already executing, I'm going to switch the execution plan to an hasJoin, because hasJoins are much more efficient when we talk about joining large data sets, in fact. And your final plan will be an hasJoin, while the default plan started out as a nested loop. Now, if you want to display a plan and you're going to use the explain plan command, which doesn't execute the statement, so you cannot have adaptive query optimization because that is runtime adjustment of the execution plan. The explain plan command will always show the default plan. So it says, if now I would carry out that select statement that does a join upon order items and product information, the optimizer says, look, I think based upon the statistics that a nested loop is the most efficient way. However, there are no statistics collectors shown in the plan because that's only used when the statement is actually being executed. Now, after the statement has completed, so has been executed, you can then see what is then actually the final plan that it has used by calling the function display cursor of the package dbmsxplan. And it might be possible that the final plan to be used was not the nested loop, but that it switched at runtime to an hasJoin, in fact. Once again, this is not going to show the statistics collector. Now, if you want to obtain more information about what is the default plan, what has been the final plan, can you show me where statistics collectors have been embedded within that execution plan? Well, what you can do is, when you're going to display the execution plan, you can add the option format plus adaptive, in fact. And there you can see, for instance, the formatted result of your execution plan. And in the node it says, yeah, but watch out, this is an adaptive plan, in fact. Now, what do you see is that it mentions inside the execution plan a so-called hasJoin as well as a nested loop, in fact. Yeah, but what you got is that this statement actually started out with a nested loop, but during execution it saw that nested loop was really not the most efficient way, and he switched to an hasJoin, in fact. Well, what you're seeing is that the nested loop and statistics collector and so on, you see that they are being prefixed with a dash. This means that this was the initial plan that has been used, but it switched during execution to an hasJoin, in fact. So with the plus adaptive format parameter, you can display more information concerning this adaptive query optimization and if this took place. Now, if you look into VLOR SQL, which is a view of the SQL statements cached inside the library cache, you will get a new column, is resolved adaptive plan, in fact, that will show whether an execution plan is an adaptive plan that has been resolved to a final plan, in fact. Now, this optimization only happens one time, because if at the first execution he adapts your execution plan from nested loop to hasJoin, for subsequent executions he will keep on using that has joined, and for the subsequent execution, statistic collectors and buffering is disabled. So in this lesson, you should have learned how to interpret execution plan, and you should have learned topics about the adaptive optimization of queries. Now for this chapter, you can make a couple of exercises that cover the utilization of adaptive plans. Workshop 6 of the SQL Tuning course for developers. So in this workshop, you will review the execution plan in several sections in an event 10,053 trace file, interpret information to understand the optimizer's decision, and learn how to use information in the 10,053 file to tune the SQL statement. So in this workshop, you're going to review the execution plan shown in the workshop guide. You're going to review it and also review several sections in an event 10,053 trace file. There are also questions on cost model, selectivity, and cardinality. You will interpret the information to understand the optimizer's decision. And finally, you'll learn how to verify the cost of a nested loop manually. So out of an event 10,053 trace file that was generated for this select statement, that performs a join upon emp and depth, this execution plan has been captured. Now I'm saying that to do the join, the optimizer has chosen a nested loop which has a cost of 4. So the question is, from where and how is the cost of this nested loop 4 derived? Now when looking at the execution plan for that select statement, the first thing that he will do is he will perform the full table scan upon table emp. This means that this is the altered table, and once he has scanned the altered table, he is going to join that with table depth, which is then your so-called inner table. Now in order to find out why that cost of that nested loop is 4, you will have to review the information needed to understand the CBU cost model. It shows you the formulas on how the optimizer calculates the cost, the single block read time, the multiple block read time, the CPU costing factor, etc. And it's those formulas that we're going to use to calculate or to derive the cost of that nested loop being 4. So first of all, what you need to do is you will have to look up the system statistics section in your event 10,053 trace file, and you will have to calculate the single block read time, knowing that the block size of your database is 8 kilobytes, and the CPU cost scale factor. So the single block read time is the I/O seek time plus the database block size divided by the I/O transfer speed, which is I/O seek time, it's 10 milliseconds, plus the database block size, which is 8 kilobytes, divided by the I/O transfer speed, which is 4096 bytes per millisecond. And if you calculate this, so the read time for one single block is calculated to be 12 milliseconds. Then you need to calculate first the CPU costing factor, if then afterwards you want to calculate the CPU cost scale factor. Now for the CPU costing factor, you take your CPU speed, which is 1999 million instructions per second, multiplied by 1000, multiplied by your single block read time, which is 12 milliseconds. This gives them this CPU costing factor of 23,988,000. And once you have calculated this, you can then calculate the CPU cost scale factor by dividing 1 by this previously calculated CPU costing factor, which gives me a value which is nearly 0. Now, the altered table cost scan, which is in my case the full table scan, it has a cost of 3. Where is that 3 coming from? Well, what you need to do is you have to, in your event 10,053 trace file, look up the section about the access path analysis for table emp. And the outer table cost, which is in this case table emp, is your I/O cost plus your CPU cost. Now what you're going to do is, in the access path analysis section of that table emp, look up the I/O cost, which is 3, plus the CPU cost, multiplied by the CPU cost scale factor. Now this CPU cost scale factor is nearly 0, so it means that you get 3 plus nearly 0, meaning, if we round this, that the cost for scanning the outer table is 3. Then what we need to do is, we have to calculate the cost for the inner table, so for scanning table depth. The inner table cost is the I/O cost plus the CPU costs. So what you need to do is, you have to look up the joining information, where he starts looking first at table emp and joins it then with table depth. Now the optimizer thinks that only one record is going to be retrieved out of this outer table. This is in our case the emp table. And then what you're going to do is, you look then at the access path, because an index is being used. I can see that in the execution plan. In fact, I see that my I/O cost is 1, plus my CPU cost is this 8341, multiplied by the CPU cost scale factor, which is nearly 0. So the inner table cost equals 1. So what is then the total cost to perform the nested loop? Well, it's the cost to access the outer table plus the inner table cost, but multiplied by as many times records are being returned by the outer table. In fact, so you get 3 plus 1 multiplied by 1 gives me a total cost for my nested loop of 4. Now, which statements regarding the nested loop join are true? Well, the optimizer uses nested loops when joining a small number of rows with a good driving condition between the two tables. Also, the cost of nested loops is easy to verify manually by using an event 10053 trace file. And a major component of the nested loop cost is the I/O cost and not necessarily the CPU cost, which in our case was always near 0. Practices for lesson number 6, interpreting execution plans and enhancements. The exercise of chapter number 6 covered the dynamic plans part of the adaptive execution plans feature in Oracle Database 19c. In this activity, you're going to use dynamic plans part of the adaptive execution plan features. The first thing that we will need to do is we will have to establish a session as user sys upon our database environment and switch to the container ORCL PDB. And we're going to grant user OE the system privilege select any dictionary. So here, if I go back to my practice machine, I log in as sysdba into my database environment, switch the container to ORCL PDB, and I'm granting select any dictionary to user OE. And what you're going to do is, in that same SQL Plus session, you're now going to establish a connection as user OE with password OE, and you're going to issue the command explain plan for this particular select statement. So connect as OE with password OE, and then execute this explain plan command for this particular select statement. And then via the function display of the package dbms explain, you're going to ask what is the execution plan that was rendered by the optimizer. Well, look, so here I'm connecting as user OE upon my pluggable database ORCL PDB. And now I'm going to call the command explain plan, and I'm asking to execute this for this particular query. And then what we're doing is, via the function display of the package DBMS expand, we can ask what is the execution plan of the last explained statement. And you see here the output stating that the optimizer says if right now you would execute this particular select statement, it's going to make use of a nested loop. That's also what is indicated within your activity guide. Now what you're going to do then, you're then going to ask to actually execute that query. So the optimizer will come up with an execution plan, which is going to be that nested loop. So what I'm doing now is I'm going to execute that select statement. You see the result is being shown. And then what we're doing is via the function display cursor of the package DBMS expand, I can ask, can you show me the execution plan of the last executed query within my session, in fact. Now we have seen with the explain plan command that the optimizer comes up with a nested loop. If then I'm going to really execute that statement and I'm asking, can you please display the execution plan? What do I see is that I'm not seeing a nested loop, but that is using a hash join. So what actually has happened? Well, it came up with a nested loop join, but while it was executing, it saw that the estimates that he has made, that they are not really accurate, they're not really up to date, and it's going to see if he cannot find a better execution, but while he's already executing, and that's where he switched to the hash join. And you can have a look in the notes when displaying that execution plan that this is an adaptive plan. So they explain here in the activity guides that the actual plan used at execution was a hash join. And I've told you that the plan has changed because the optimizer realized during execution that the number of rows actually returned was much larger than expected. Multiple single column predicates on that order items table caused the initial cardinality estimate to be incorrect. The misestimation cannot be corrected by extended statistics because one of the predicates is a non-equality predicate. So he started out with a nested loop, but during execution he switched to a hash join because he saw that this is a much better method to execute that select statement. Now, how can you confirm whether the plan was changed due to the dynamic plan feature? Well, by looking into VLOR SQL and looking into the new column is resolved adaptive plan. I show you here the select statement that you should execute to find out if that execution plan that has been captured, if it's a resolved adaptive plan. And that's what you're seeing here. Is I'm carrying out this select statement upon VLOR SQL, calling the new column is resolved adaptive plan, and I'm seeing that for that select statement, the column indicates that this is a resolved adaptive plan. So the plan was changed during execution due to this dynamic plan feature.